באתי להגיד, כאילו זה לא...
גיליתי שזה בעיה, סתם, אני לא מכיר.
לא מוחזב ממך, גיד.
לא, ממש לא. להפך, אבל...
מהקצת רמה הזאת.
אני לא יודע להגיד את זה.
אני נוסע פרק של פרנץ' כמעט כל לפחות פעם בשבוע.
אני גם. נוגע, אתה יודע קיצור תמיד, כן? כן. היי, שרות.
ולפעמים זה אותו פרק שהייתי שבוע אחת לפני.
שיט, שוב שכחתי את המחת. ליאור יש לו מחק?
מחק?
זה בסטיק.
זה סטיק? זה עוד 5 ילדים, איך אוכלים את זה?
יש לי כאילו כמה צריכה למחוק, הרבה או קצת, יש לי כזה.
לא, עדיף שיהיה לי מחק כזה, כי אני מוחקת הרבה בשיעור. כל מה קוראים מסביב, אני... Have you had an eraser that you don't need for the class because I forgot mine?
She needs you to have it.
Can't you just...
She needs you to have it.
No!
You know what you need?
כן, זה ככה.
You need a Shabbat. What's that what you need?
את שבת.
That's a great translation.
I don't know what it means.
זה מחיק.
אם אתה כותב, I can write? I will use it during class. It's your notes. Okay. So it's a fair deal.
לא, זה לא העיתים של כאילו שאתה למחוק.
כי אז זה כאילו ממש רמאות, כאילו כתבתי ומחקתי, אז אפשר?
לא, זה עץ שנמחק לבד, כאילו, אחרי כמה זמן.
זה היה פעם בקסם, קראנו לזה. כשהיינו כותבים על היד, וככה היינו מעטים בשיעור.
אז לא, עכשיו שעשי זה כסוף טוב, משהו שבת כאילו, כסוף טוב, הרבה נראות לא נשאר, אז הרבה פחות בעייתי.
מה
זה
כותב?
יופי. שבתקי וכאלה.
מה זה שבתקי?
כאילו,
כן,
ואז זה חשוב, אז במותג שחוזר על זה. זה גם עתיד לדעת?
כן, טוב.
אני פה לשם.
אתה ברחת?
אני ברחתי.
לא נעלם.
לא ממך.
גיא. מה שלומך? שלומי, לא. שלומי טוב. אתה לא צריך להגיד שלומי, יכול להגיד סתם טוב.
כן, אני יודע, אבל...
יש בדרך כלל לא אומרים שלומי.
אני יודע, אבל זה לא יצא ככה.
לא יצא. אז מה שלומך? זה השלום שלך.
זה המון זמן, ממש המון זמן, כי את... לא,
אוקיי. למה לא בלתי סביר, כל הזמן קצת.
זה לא פתח כל הזמן.
וואי, זה יכול עכשיו ל-10-20 שעות.
מה, פעם?
אז אמרת לפני שתי.
אז אמרתי את 21.
כאילו, השיעור היה. מה אתה עושה? חצי?
Okay, good afternoon. Is anyone planning to take notes? Nobody taking notes? One other thing, while you think about taking notes, we lost some time due to ISFN, and I think we need, in order to finish enough things next week, because we have just 2 more weeks, 1 extra hour. So what I was thinking is doing another extra hour on Thursday next week before the regular time at 11. Does this work can this work for most people?
It means we have 5 hours time.
I know, but it's just one time. Okay, so this is the current plan. I will send a notice on it. I'm open to other suggestions, but I think it will be difficult to find a time separate from the regular. Okay, so last time we discussed encoding of a multidimensional set of inputs by 1 output unit. And I remind you that after formulating the problem, understanding how we need to formulate the problem, eventually the mathematical formalism told us that the best choice, the best projection of the multidimensional inputs to choose is the first principal components of the inputs. And the crucial ingredient there was the assumption that there is isotropic input noise. There's input noise which is independent in the different input units, identical in the statistics, additive. And then the reason why the principal component, the first principal component is the best projection is because that is the projection such that after the projection you get the largest signal to noise ratio. The projected variable has the largest component which is signal compared to the component with the noise. The noise component doesn't depend on the choice of the direction of the projection, whereas the signal component does depend on it. Now, I want to mention briefly that there are other formalisms that can give rise to the same conclusion that the best projection is the first principal component. And I want to mention one which is important. Perhaps some of you have encountered it if you took. Is there anyone here who took Jonathan's course in cognition? Yeah. So I think Jonathan in that course discusses the other formulation of the problem. And it's instructive to see it. So I will start with that. And after we do that, we will discuss a learning rule, and then hopefully we'll already start today to discuss encoding by multiple output units and not just one output unit. So let me write down the title. So the idea is the following. Suppose that we have a set of input units, xi, and they have some statistics, okay? And we project them linearly into one output unit. Y. So let's call this vector x. And now the idea is that our goal is to simply reconstruct the inputs based on this single output unit. So what can we do? We just need to multiply the value of this output unit by some choice of a vector, right? But anyway, this is what, and my assumption is that this is also going to be linear. So we have n. We want to reconstruct an n-dimensional vector based on the output unit in a linear fashion. We will write this in a moment. So this will be xi tilde. And our goal is to make x tilde as close as possible to vector x tilde, the vector, as close as possible to the vector x. Of course, you can imagine how you could also generalize this to several output units, but for now we discuss just one. So one thing to note is, you know what, one thing to note I'll mention later. So let's just formulate this a bit more clearly. Our goal is to have to optimize the reconstruction error, meaning that, of course, we have to decide how to quantify it, but we will use mean square. We'll use the difference of squares. So this is sum over the element of the vector of xi tilde minus xi square. That's what we want to minimize. I need to still write down the relationship between y and xi and the xi tilde to yi. These are the. We'll also define the parameters of what were varying. So y is some linear combination of the x's, and the xi tilde. So in vector notation, y is w transpose x, where w is a vector of weights, and the xj tilde is equal to w tilde j, some other principal weights, times y. Okay, so this is what I mean by saying that this is linear, and so in vector notation, x tilde vector is y times the vector w tilde. Okay, so now it's and I could also write this as w transpose x times w tilde. So eventually this defines the relationship between the input and the reconstructed output, and we want to make that as close as possible to x in this sense. Okay, now what are we averaging over? When I write here an average, the statistics of the inputs. This is really over the statistics of the input p of x. So one thing to note in this formulation is that I did not assume any noise, not in the input, not in the output. This problem is well defined, even if you don't include any noise. The limitation in the ability to reconstruct x fully from x lies in the fact that we perform this dimensionality reduction and in the architecture, the linear architecture. And so I will not solve this explicitly. Okay, I just want to mention this way of thinking about dimensionality reduction. And the solution, I'll just tell you what is the solution. So if you try to optimize, you reach the conclusion that w and w tilde should both be proportional to the first principal component of the inputs. Of the inputs, the input statistics. So essentially, the best, if the rules of the games are defined as they are here, the best thing to do is to project the input on the direction in which it has the maximal variability, and then expand back by simply taking the coefficient of this projection and multiplying it back by the first principal component vector. Now, can you tell me why that's the case? why this is better than other, say, principal components. Okay, so we discussed information previously, but here we'll not discuss it. We're not formulating this in terms of information theory quantities. So why is it better to do this with, say, the first principal component versus the last principal component?
Because you preserve as much variance as you can.
Exactly. So our measure is a measure of variance, of our mean square distance. We preserve as much as a variance. Where the reason x is not the same as x, you can think about this as long as, if you imagine that what we're doing is projecting on several principal components and just extracting one of them. So we're preserving one of the components in the projection of x on the principal component, and therefore the reason that x tilde is different from x is that we're throwing away all the other components. So it's better to throw the ones that have little variance. That will make the difference between x and x tilde smaller than if we throw away the components with high variance. So we keep the one with the highest variance. And this would generalize to a situation where we have several output units. Okay, one other thing the next thing that I want to do is discuss a learning rule called Oya's rule. I will also do this relatively briefly. And so the question is the following. Suppose that we have a neuron which is receiving n inputs, and there is a freedom to optimize or to adjust the weights between this neuron and its inputs. We want to ask whether there is some rule, plasticity rule, which is reasonable, it's local, it acts only depending on in each synapse depending on the activity of the input, the presynaptic activity, the postsynaptic activity, and that will make the neuron learn to extract the first principal component. And so it turns out that there is such a rule, and this is what we will discuss. So as before, we have a set of inputs. They project to one output unit. Y is equal to sum over I, Wi, Xi. Okay, and I will just write down the rule and argue why this rule will eventually, the learning rule, which is just these weights, will eventually choose the weights that will extract the first principal component. So the learning rule is the following. So imagine that this neuron is presented by inputs sequentially, and after each presentation, we change each one of the weights as follows. So what I mean by the change in the weights, let's imagine that I designate by Wn the weights after the nth presentation. So this will be the n plus 1 weights minus the nth weight. And the rule is, well, I'll first write one version of it, and then I'll correct it a little bit. So in the initial version, what I'm going to do is I'll have some learning rate, and I'll take the output of this neuron, yn, and multiplied by the input from the ith, by the ith input at presentation n. Okay? So this is a classic kind of learning rule for a synapse. It's a Hebbian learning rule. The change in the synapse, in a particular synapse from this neuron to this neuron, is proportional to the product of the activity of the output neuron and the postsynaptic neuron and the presynaptic neuron. That's what's written here.
It's not some correct activation. That's what happens in
What?
the yn is not some correct supervising.
No, there's no. This is completely unsupervised. This is an important point. We discussed supervised learning a lot in the first few weeks of the course. And this is an example of a learning rule which is completely unsupervised. We're not telling the system that it's doing well or not well. It's just observing its inputs and adjusting the weights. Now, there's one problem with this learning rule. Which is that if we would apply something like this, what will typically happen is that the weights will either explode or go to zero. Okay? We really care from the point of view of what I want to show you that this learning rule is doing. What we really care about the direction of W. We don't care so much about the magnitude, but nevertheless, it doesn't make sense to apply a learning rule that will just make the weights explode. So what we're going to do is to adjust this rule in one more way. And so let me call that, just let me see how I denoted it here in my notes. Okay, I will just rewrite the rule. So we will not do this. Instead, what we will do is delta Wi, or I will write it like this: Wi n plus 1 is equal to Wi n plus this addition, eta y n xi n. But now I will divide this by a normalization factor. And I will choose a normalization factor such that the L2 norm of W will always be the same. Without loss of generality, I will just make it 1 all the time. So I will just multiply by the sum over all the neurons of this thing, Wj n plus eta y n xj n squared. So you could imagine, if you wish, that we do this in 2 steps. We first add this, do this thing, do this, and then we multiply all the weights by a factor set such that the sum of the squares of W will be equal to 1. But from the neurobiological standpoint, this means that there is some interaction between the weights going into the neuron. So now the rule is not completely local at the level of each synapse. It's local at the level of the output neuron and the synapses projecting into it. And we could imagine that something like this is happening because there is some overall normalization of the total weights going into each neuron. It's conceivable to imagine that there are processes in the neuron that adjust the relative sizes of all the weights, synaptic weights projecting into the neuron. Okay, so this is Oya's learning rule, and now we want to understand. Yes.
Maybe you answer it later, and I'm interested. Is this rule assuming the mean of x to be 0? If the mean is not 0, do we need to subtract it somehow or not?
Let's see. I don't remember, and we need to just see what we get. My guess is that yes, it's a good point, but we will. Let's see. Okay, so now what we want to do is to analyze what this rule is doing, and we will assume that the learning rate, as we usually do, that the learning rate is small. But as you will see, we will need to make that assumption in several different ways. So I will discuss that when we get there. So the first way in which I'm going to assume that eta is small is just in a way that will allow me to expand this expression for small eta. So I imagine that I write the Taylor expansion of this for small eta. And when I want to do that, when I do that, then let's just think about the denominator here. 1 over square root sum over j wj n plus eta yn xjn square. Let's start to treat this and see what this, I want to expand this to first order in eta, then I will need to still multiply it by the numerator, but let's first deal with this part. So the first thing that I am going to do is that I have here a square, and so I will write just the first order terms in eta of this expression. So this will give me 1 over square root of sum over j, w j n squared okay, so this will be one term, and then I will have other terms which come from the product of this and this. So this will be plus 2 eta sum over j wjn yn xjn, right? And I'm neglecting the second order, the term which is quadratic in eta, because I want to do an expansion only to first order in eta. Now this thing is equal to 1, because this is the sum of the weights in the previous step, and we always normalize them, right? So this is 1. Okay, so now sum over j yjn times xjn, what is that? Sum over j wj xj, it's yn, that's by definition yn. So actually what is written here is yn to the power 2, yn squared. This is this sum. So overall, what we get therefore is 1 over, well, let me write a approximate equality. So this is 1 over square root of 1 plus 2 eta yn squared. There is a term second order in eta which I am not writing. And now if we want to write what is this to first order in eta, this is through the Taylor expansion of 1 over square root of 1 plus x. This is going to be equal to 1 minus eta yn squared. And of course there are higher order terms, but I don't care about them. I neglected anyways terms of order eta squared. Okay, so now we just expanded the 1 over the denominator, and we need to multiply this by the numerator. So wi n plus 1 is equal to win plus eta yn xin multiplied by 1 minus eta yn squared. And so I need to now collect terms of up to first order in eta. So this is equal to win, and then I will have two terms of order eta. Both of them are proportional to yn and to eta, so I have eta yn times xin minus something here is missing. Something times w. Okay, so times nothing is missing. When I take this term, it's multiplied by w. So here, this comes from 1 times this. This is what I already wrote. And then there is a term which is win times this. So this will give me minus win yn. Okay. So this is one way in which we're using the fact that there's what?
Why should the y and also be different?
It's just that this term involved w, eta, and yn squared. So that
Yn is
okay. So the yn was squared. Okay, let's continue here. Okay, so now I want to ask, what is this rule doing on average? We are going to present this rule with many, many examples. And I want to ask, what is this rule doing on average to the change in W? So let me write that down. The average change in Wi is given by eta times, I need to average the terms that appear here. So x is a random variable, y is also a random variable that depends on x and the weights. So I have here y xi minus the second term is wi average of y squared. Now, at this stage, what am I averaging on? I'm averaging over the possible realizations of x. What I really want to do is to average over time, to average over many presentations of the input. But there's a small issue here. As we're presenting more and more examples, the weights are constantly changing. So I can think of this average as an average over time instead of an average over instantiation of the inputs only if the learning rate is sufficiently slow. So the learning rate needs to be sufficiently, and this is a more crucial assumption about slow learning rate than what I did here. I have to assume that the learning rate is sufficiently small that the change in W is determined from many, many small steps, and in each one of them I can still think about the weights as if they're constant. And so the system, this neuron, this system of synapses of this neuron has a chance to sample the distribution of the inputs over a time scale or number of presentations during which the weights are still not changing significantly. So that's an assumption. I'm going to assume that. So this is the essential assumption of slow learning.
But I still don't understand how do you just change it from an average over the distribution of x to time?
So imagine.
That's an assumption, but not how you.
So imagine that I would actually not modify the weights. Okay? Imagine that I would perform this rule and just in my bookkeeping write down what are the changes that should have been made into the weights in each one of the steps without actually modifying the steps. Then clearly, when we do this many, many times, it's as if I'm averaging over the statistics of the input, right? Now, in fact, the weights are constantly changing. But if they're changing sufficiently slowly, I could choose a batch, I don't know, 1,000 examples, and over, let's say that over 1,000 examples, the weights are still not changing significantly, then it's as if I didn't change them. Then I can write down that the average change, it's just that this thing is, in one presentation, this thing is very noisy. It depends on the particular inputs. But if we do it many times, we're already averaging over the statistics of the inputs. Does this make sense?
Yes, but where time gets into.
Time, I mean just the number of presentations. Okay, that's what I mean.
Why can't you just average on time?
Because again, if I'm not allowed, if I just imagine, by time I mean again number of presentations. If I average over 1,000 presentations, maybe from one presentation to the next, I cannot think about this W as being fixed. So note that when I wrote here average, I took the average only on this, and I imagined that the W is just given. That's true for one presentation. From one presentation to the next, the W is simply the W of the previous presentation, and I'm allowed to do this. But if I want to replace this, think about this as an average over, say, 1,000 presentations, I cannot do it in this way. I cannot just put the average only on this. The weights are changing from one presentation to the next, depending on all the inputs that have been seen. Nevertheless, if the learning is sufficiently slow, I can neglect that fact, and that's what I'm doing. Okay? So,
Sorry, you're trying to gather the average change in the weight.
yes.
Don't you assume that W is constant?
Yes, this is a little bit tricky, and it's very similar to what we did when we discussed stochastic learning. This is stochastic learning. We discussed stochastic learning previously in the context of supervised learning, right? And we had the same issue there as well. We wrote down, what I argued is that if the learning rate is sufficiently slow, then the learning becomes more and more deterministic, in the sense that, also we look at this. So maybe on one presentation, the change in W can vary wildly according to the example that has been presented. But if instead of that I have 1,000 presentations, let's imagine that instead of doing one step like this with a certain learning rate eta, I will do 1,000 steps with an eta which is smaller by a factor of 1,000, then the mean will be the same, but the variability will already be averaged out. So there will be an average change. The average change will represent well what is the change in the weights after enough presentations. That's the idea. Okay. You're not satisfied by my answer, so we can discuss it. We can discuss it later. But it's the same idea that happens whenever you average over many independent trials. If you toss a coin, then one time, then there's an average of half that it will probably, on average, on one case out of two, it will fall on one side. But on average, it's very variable. And if you toss it 100 times and count how many of them you got one side, it will be much closer to half than if you do it once. Okay, so anyway, so what I'm arguing is that for slow learning, I'm going to write something which involves time in it. But time just means the number of presentations. I can write that the change in the weights over time is proportional to eta times the average of yxi minus wi y squared. And note that this, on the right-hand side, involves the weights in more than one way. It explicitly involves, in what I wrote, the weight wi appears here, but all the weights appear in how y is determined by x. So the dependence on w is more complicated than it appears just by looking at this wi. And now what I want to ask is, what does this learning rule do? So again, note that by making the assumption of slow learning, I replaced this stochastic set of changes in W, which is what is really happening in each presentation, with a deterministic set of differential equations. The change in W depends on the change in Wi depends on all the W's through this equation, which involves the statistics of the inputs and the way that y is related to x through these W's. You'll see in a moment what that means more clearly. And now I want to ask, what do these dynamics do for the weights? So I can ask first, do these dynamics lead to some steady state of W? If so, then at steady state this becomes 0, and that means that this expression must be 0 for all i's. So if there is a steady state, it will obey that the average of yxi is equal to wi y squared. But now I want to write down explicitly how this depends on the weights, and this is what I mentioned earlier. I need to write down how y relates to the x's through the w's. So so this is sum over j. Y is sum over j wj xj.
No, sum.
Ah, yes, thanks. But here it's okay, right? Okay, so y is sum over j xi xj, wj xj. The w's are not, the average is over the statistics of the input. So the w I can take out of the average. So I will have here sum over j wj xi xj. Right? That's what I have in the left-hand side. And here I have y squared, which is the square of wj xj. So this has to be equal to sum over I and j, wi, wj, xi, xj. I is not a good index here because I is already, so sorry, so let me, so no, I think I made a mistake here. So this is wi, and now here I need to sum over two indices. This is sum over, say, k, wk, xk, and I need to take it to the power 2. So I will have here sum over k and l, wk, wl, average of xk, xl. This is not sufficiently clear. xk, xl. Now, you know what, maybe I will use instead of k and l, I will use j and k, okay? J and k will be better. The only index that I need to worry about is I, which appears explicitly here. wj, xk, wj, wk, xj, xk. Okay, so now this, by definition, is the covariance matrix of the inputs, assuming that there's zero mean. So this is where the zero mean is important. So if the inputs are not zero mean, in order to get what we want, we need to subtract the mean first. And so this is what we call Cij. Okay? And this is what's the same thing. This is Cjk. So so what we got is that sum over j w j Cjk is equal to wi times sum over j and k, wj Cjk, wk. And so in matrix notation, what we got is that C, the matrix C, times W. Note that this matrix is symmetric, so I could write it also as C times W. Is equal, here we have, all this is a number, right? All this is a number. So here we have a vector with the vector W multiplied by this number. And that number is W transpose C W, and that multiplies W. And again, this is just a number. Okay, it will take me just a few more minutes to finish. What does this equation tell us? Yeah, this equation means that W is an eigenvector of C. an eigenvector of the covariance matrix, by definition, is one of the principal components. So what we concluded so far is that at steady state of these dynamics, the weights reach a form which is one of the principal components of the covariance matrix, but we don't know which one. In fact, any one of the principal components of the covariance matrix is a steady state of these dynamics. Okay? So now the question is whether the dynamics will actually reach one of these states. So all principal components are steady states, but there is something else that we need to know about the dynamics in order to hope to find which one the system will go to. What is that? Stability. So what we need to do next, which I will not do, this will be an exercise, is to analyze the stability of these dynamics around each one of the steady states. Okay? And it turns out that these dynamics are stable only around the first principal components. Meaning that if it's true that if we will put the weights such that they're exactly equal to any one of the principal components, and in the limit of the deterministic dynamics, the weights will change there. But as soon as there is some stochasticity, and we have stochasticity because the dynamics are actually never like this, they're always stochastic. Once we take a small perturbation from one of the other principal components, that would be unstable. And so from that we can conclude that the system will eventually go into a set of weights which is the first principal component. Yes?
Maybe I missed something. How did we show the steady state is a principal component, but not that all principal components?
Yeah, but you're right. So in order to convince yourself that that's true, you need to check, given that W is a principal component, that this becomes consistent. The number that appears here is consistent. So if you need to check that if C times W is some lambda times W, and you know that that lambda is one of the eigenvalues of C, that by definition is the fact that the meaning that W is that principal component. You now need to see that if you plug this in here, this will be consistent. The number that will appear here and here will be the same, the prefactor of W. So but it's very easy to check. Here you'll have lambda times W, right? Here you'll have a lambda times W multiplied by W, but remember that W is normalized, so this is just lambda, and again times W. Okay, so indeed, if W is any eigenvector of C, this equation is obeyed. Okay, and you can go backwards, and this equation will be obeyed. Okay. So again, the next crucial step in understanding why this rule picks up the first principal component and not the others is the question of the stability. And I will leave that as an exercise. I was asked to remind you to fill in the teaching survey, and I'll see you on Tuesday. The first principal component. זה הכותרת של מה שעשינו בהתחלה. כן, כן, כן. הסיפור הזה של הביצוע. נכון, אז בעצם הדרך לחשוב על זה, נניח שהייתי מתחיל את לא, אז באמת, דיברנו על זה גם כשעשינו את הלמידה המפותחת. ככל שמקטינים את קצב הלמידה, יש לזה גם חיסרון, הלמידה זה יותר זמן. כדי שגם זה יפסיק להשתנות, אם נגיד את הכתיבה מהבעלה. בסדר, נכון. עם 100 זמן כדי ש-W ישתנה בסדר גודל. אז אני חושב על זה, אני חושב על זה, באופן מחשבתי, נחשוב על זה, נראה שמתקין את W, את eta, אבל להסתכל יותר זמן קדימה בעצם. מתקין את eta פי 100, להסתכל אבל על כמה W השתנה אחרי פי 100 צעדים. אז כשאני עושה את הטריק הזה, כשאני מתקין את קצב הלמידה ובהתאם מסתכל יותר זמן, בממוצע השינוי ב-W בשני המקרים אותו דבר. ההבדל הוא שבמקרה שבו עשיתי נגיד צעד אחד, יש הרבה מאוד וריאביליות בכמה W ישתנה בצעד אחד. זאת אומרת, ב100 צעדים התממשו על הרבה מאוד אינפוטים, ולכן הסטיות מסביב לממוצע הם יותר גדולים. אבל זה נכון, עכשיו, יש פה שני מרכיבים. אחד, מה שאני צריך גם להניח זה שאתה הוא מספיק קטן, שבאמת על 100 צעדים האלה, W עוד לא הספיק כל כך להשתנות. זה מה שמבלבל. אני מנסה לחשוב איך להגיד את זה אחרת, כי אני כל הזמן כאן חושב בשעה מסוימת, נכון, אבל יש פה כמה דברים שונים שאמרתי. אחד זה שאני מחליף בעצם, פה אני החלפתי את ה... זה רק הממוצע של השינוי ב-W. פה אני כבר כתבתי שזה באמת השינוי ב-W. זה לא נכון, זה לא באמת השינוי ב-W, אבל אם הווריאביליות מסביב לשינוי הזה היא מאוד קטנה, זה בסדר. אז בצד אחד זה אף פעם לא נכון. בצד אחד השינוי ב-W הוא מאוד וריאבילי בהתאם לדוגמה שראינו. אבל אם הייתי חושב על מספר מספיק גדול של צעדים, זה כבר לא היה נכון. אני אנסה להסביר את זה. שוב, מה שאמרתי קודם, נניח שבפועל לא הייתי משנה את זה. אוקיי, הייתי רק צובר כאילו את השינויים שהייתי צריך לעשות. אבל אם את מסכימה איתי שאם אני אקטין את W פי 1000 ויקח 1000 צעדים, את eta, אני אקטין את eta פי 1000 ויקח 1000 צעדים, בממוצע השינוי יהיה אותו דבר כמו השינוי בצד אחד. מצד שני, הווריאביליות תהיה הרבה יותר קטנה. אני ממצא על הרבה דוגמאות שונות. זה כמו שכשתספרי באיזה אחוז מהצעות המטבע אני אעשה לצד אחד, אז תעשי את זה 1000 פעם, זה יהיה הרבה יותר קרוב לחצי, מאשר אם תעשי את זה 10 צעדים. זה בסדר החלק הזה? לא, זה חשוב, כי אנחנו צריכים קודם כל תחלט את משהו. אם לא הייתי בפועל משנה את W, והייתי עושה הרבה יותר צעדים עם קצב למידה יותר איטי, אז בממוצע הייתי מקבל את אותו שינוי, אבל הווריאביליות סביב השינוי הזה הייתה יותר קטנה. זה דבר אחד. עכשיו אני אומר, אני יכול, אם קצב הלמידה הוא מספיק איטי גם, שבפועל השינוי שקורה ב1000 צעדים הוא מאוד קטן ביחס לגודל של W, אז אני יכול להזניח, ב1000 צעדים אני עדיין יכול להזניח את העובדה של W ישתנה. אז הארגומנט הוא שאם השינוי קצב הלמידה הוא מספיק איטי, אני יכול לקחת מספר גדול של צעדים שבהם עדיין W לא מספיק להשתנות, ועל פני המספר הגדול של הצעדים האלה, השינוי הממוצע הוא כבר מתאר מאוד טוב את מה שיקרה בפועל, כי הווריאביליות סביב השינוי הממוצע היא קטנה. כי אם W כן היה משתנה, אני לא יכול לחשוב, מה שכתוב פה, כתוב איזשהו W, אבל בכל צעד W משתנה. אם אני צריך להביא, אני כאילו מזניח את העובדה שהשינוי ב-W בצעד ה-50 הוא גם תלוי במה היה, הוא בעצם תלוי במה היו האינפוטים בצעד 49 ובצעד 48, כי בכל אחד מהצעדים האלה ה-W עצמו השתנה. נכון, אז זה מין קירוב כזה, שאני יכול להגיד, הייתי יכול לקחת באץ' של 1000 דוגמאות, אם קצב הלמידה הוא מספיק איטי, אז ב1000 ה1000 דוגמאות האלה אני יכול להזניח את העובדה ש-W תוך כדי משתנה. נכון. אז ככל ש-eta יותר קטן, יש או מספר יותר גדול של דוגמאות שבהם אני עדיין יכול להניח ש-W לא מספיק משתנות.
גדל במספר הדוגמאות באופן כללי יותר קל.
נכון, נכון. אז זה מאוד נכון. אז ככל שקצב הלמידה יותר איטי, eta יותר איטי, בהתאם באופן פרופורציוני, ייקח יותר זמן ללמוד.
נכון, ואז יבחר.
אבל מצד שני הלמידה יותר דטרמיניסטית, פחות יש בה, אני יכול להיות יותר בטוח מה יהיה התוצאה של הלמידה הזאת אחרי מספר גדול של צעדים.
אז הממוצע צריך להיות רק על המסעות האלה שבו
אני אוהב האינטואיציה.
נכון, נכון. בסופו של דבר גם פה אני תיארתי משוואות שמתארות שינוי ב-W שהוא תלוי כאילו בהתקדמות לאורך ההצגות.
זה מורכב ממש.
בסופו של דבר ה-W משתנה, ותוצאה מזה שהוא משתנה, מה שרשום פה כן משתנה. אבל הטיעון הוא שאני יכול להכניס את המשוואות הסטוכסטיות שפה רק כתבתי ממוצע, אני יכול לדמיין כאילו שבכל צעד W משתנה באופן דטרמיניסטי על פי המשוואה הזאת. עדיין, השינוי פרופורציוני לאתה, כשאתה מספיק קטן הוא באמת לא משתנה, הוא משתנה נורא קצת, אבל השאלה היא איך הוא מתפתח. מה שמופלת לה איך הוא נראה.
הראשון שדורק מספר, עכשיו כולם
יש פה, מצד אחד אומר שלא משתנה, מצד שני אומר שהוא כן משתנה. לא משתנה במובן זה שהאתה כפול כל מה שרשום פה הוא מאוד מאוד קטן ביחס, אפילו אחרי מספר גדול של צעדים, הוא מאוד קטן ביחס לצעד שלו עצמו. לכן כאן אני יכול להזניח את העובדה שהוא משתנה.
כולם מתייחסים לשש שעות דורוקים.
משתנה, כמובן אם לא משתנה, לא כל הזמן עבר מעניין.
זה כולה מעט.
דורות המידע הזה.
העוגן יכול להיות 7 או 8.
נכון, אז אני אומר שוב, השאלה היא כמה דוגמאות צריך לקחת עד שאני לא אוכל להזניח את השינוי ב-W. אני טוען שזה, מספר הזה הוא יותר גדול ככה שאתה יותר קטן. נכון? ומצד שני מה שאני מרגיש, נכון, הייתי בעצם צריך להגיד שזה כאילו הממוצע, לא הדוגמה. דוגמה אחת, תמיד השינוי הוא לא סטוכסטי. אבל אני אוכל, ככל שהייתי יותר קטן, אני יכול לקחת, לכן אני כבר כתבתי פה איזה דוגמאות שהייתי קצת הזמן שלי זה כבר 1000 דוגמאות. עכשיו נקטין את eta פי 10, אז אני יכול עכשיו לקחת 10,000 דוגמאות. ככל שהייתי יותר קטן, אני יכול לקחת פרק של יותר ויותר דוגמאות ולחשוב על באינטרבל הזמן הזה, בבאץ' הזה של הדוגמאות, לחשוב על W שעדיין לא הספיק להשתנות לצורך החישוב הזה.
לא, אני לא מבין,
בכל הדוגמאות כולן, בסופו של דבר עד שאנחנו מגיעים ל-W, כמובן שמשתנה.
אני לא יודעת טרמינולוגיה זה משהו נמוך.
נכון, הייתי צריך לכתוב, אם הייתי רוצה לכתוב את הכל בצורה יותר מדויקת, הייתי צריך לעשות משהו דומה למה שעשיתי כשדנתי בלמידה מפוקחת בסטוכסטיק לרנינג, לשאול בעצם מה הממוצע של השינוי לפני n דוגמאות. אוקיי, ככל ש-n יותר גדול, אם W לא משתנה, אני יכול להגיד שהממוצע הזה כבר מייצג באמת את השינוי, זאת אומרת שהווריאביליות מצד שני, ככל שאתה יותר קטן, אני רשאי לקחת יותר ויותר דוגמאות שבהם עדיין W לא מספיק להשתנות. אז זה פחות או יותר עדיין הדבר. אולי מה שצריך לעשות זה שתעזבי, זה מה שעשינו עם הסטוכסטיק גרדיאנט מה שגם שם זה
היינו ממש באותו קיץ, כאילו בוועדות מים.
נכון, אני יכול לחשוב על זה כאילו שהרבה מאוד צעדים W עדיין לא מספיק לשנות ולכן הוא כן משתנה, הוא פשוט הפרופורציוני לאתה.
זה היה מקרי.
הוא משתנה לאט. נכון. הייתי יכול לקחת את הבית של הדוגמאות שלי
זה לא רק יותר מדויק,
ולחלק אותו להרבה שבכל אחד מהם יש איזשהו מספר של דוגמאות.
קשה לשמוע. אין דוגמאות.